Good day, everyone. My name is Anjusette Binanez from 8831, and the topic that I'm gonna tackle is about slatted waveguide antennas. So let's continue. So first, we're gonna tackle about the fundamentals or the antenna fundamentals. In a wireless communication systems, an RF signal generated by a transmitter is sent into free space and eventually picked up by a receiver. The interface between the transmitter and the free space is the antenna. So the function of the antenna are firstly is the transmission of the signal, which is the radio frequency electrical energy from the transmitter is converted into electromagnetic energy by the antenna and radiated into the surrounding environment, which are the atmosphere, the space, and the water. The second one is for the reception of the signal. Electromagnetic energy impinging on the antenna is converted into the radio frequency electrical energy and fed into the receiver. So a transmission line, like an antenna, is made up of a conductor or conductors. However, the transmission lines, unlike antennas, do not radiate radio signals efficiently. The configuration of the conductor and the transmission line is such that the electric and magnetic fields are contained. The closeness of the conductor keeps the electric fields primarily concentrated in the transmission line dielectric. In Figure 1a shows the electric fields associated with the coaxial cable, and the Figure 1b shows the magnetic fields associated with the coaxial cable. The electric fields line are fully contained by the outer shield of the cable, so none are radiated. The direction of the electric fields reverse one per cycle. So letter A is the electric fields and letter B is the magnetic fields. Next is the introduction to the slanted waveguide antenna with slanted waveguide antenna designs. A slat antenna consists of a metal surface, usually a flat plate, with one or more holes or slat cut out. The shape and the size of the slat, as well as driving frequency, determine the radiation pattern. Slat antennas are usually used at UHF and microwave frequencies, at which wavelengths are small enough that the plate and slot are conveniently small. At these frequencies, the radio waves are often conducted by a waveguide, and the antenna consists of slot in a waveguide is considered or called the slatted waveguide antenna. The slatted antenna arrays used with the waveguides are popular antenna in navigations, radar, and other high frequencies system. They are simple to fabricate, have low loss or the high antenna efficiency, and radiate linear polarization with low cross polarization. These antennae are often used in aircraft because they can be made to conform to the surface in which they are mounted. The slots are typically thin or less than zero point 0.1 of a wavelength and zero point 0.5 wavelength long at the center frequency of a operation. The slot on a waveguide will assume to have a narrow width. Increasing the width increases the bandwidth. Recall that the fatter antenna often has an increased bandwidth. The expense of a larger width is higher degree of cross-polarization. The fractional bandwidth of a thin slot can be as low as 3 to 5%. Wide slots can have a fractional bandwidth on the order of 75%. An example of a slotted waveguide array is shown in Figure 2. Dimension given by the length A and width B. The position, shape, and the orientation of a slot will determine how or if they radiate. In addition, the shape of the waveguide and frequency of a operation will play a major role. To understand what is going on, we'll need to understand the fields within the waveguide first. So next is the waveguides. So waveguides acts as a high-pass filter in the most of the energy above a certain frequency, or known as the cut-off frequency, that will pass through the waveguide, whereas most of the energy that is below the cut-off frequency will be attenuated by the waveguide. Waveguides are often used at the microwave frequency, which is greater than 300 MHz, with 8 GHz and above being more common. Waveguides are wideband devices and can carry or transmit either power or communication signals. An example of hollow metal rectangular waveguide is shown in the following figure, or the figure 4. And waveguides can bend if the desired application requires it, as shown in the following figure 5. Here, you can see how it bended. Next is the narrow slot. Radiation occurs when the current must go around the slot in order to continue on their desired direction. As an example, consider a narrow slot in the center of a waveguide as shown in figure 8. If the slot are displaced from the center line as shown in figure 8, the x-directed current will not be zero and will need to travel around the slot, hence radiation will occur. Note that the distance from the edge will determine the magnitude of the current. As the result, the power that the slot radiates can be altered by moving the slot closer or farther from the edge. Next is about the figure 9 here. If the slot as shown in figure 9, the slot will disturb the Z component here, of the current density. This slot will then radiate if this slot is displayed away from the center line, and the amount of power that it radiates can be adjusted. Just like figure 9, figure 10 rotated slot will radiate too. If the slot is rotated at an angle about the center line as shown in figure 10, it will radiate. The power it radiates will be a function of an angle phi that is rotated, specifically given by sine squared phi. Note that the Z component of the current is still responsible for radiation in this case. The X component is disturbed, however the current will have opposite magnitude on either side of the center line and will thus tend to cancel out the radiation. The most common slotted waveguide resembles that shown in figure 2. The front end is where the antenna is fed. The far end is usually shorted, which is enclosed in metal. To begin to analyze the antenna of figure 2, let's view the circuit model. The waveguide itself acts as a transmission line, and the slots in the waveguide can be viewed as a parallel shunt admittances. The end of the waveguide is short circuit, so a rough circuit model is shown in figure 11. This part is the short-circuited part, and this side is the slotted element that um, that space a distance L from each other. They will be given in terms of guide wavelength, which is the wavelength within the waveguide. The guide wavelength here the lambda sub g, is a function of the width of the waveguide, A, here, A, and the free space wavelength. Predominantly one mode, the guide wavelength is given by lambda over the square root of 4a squared minus lambda squared. The distance between the last slot and the end is often chosen to be a quarter wavelength. Transmission line theory states that the impedance of a short circuit, a quarter wavelength down a transmission line, is an open circuit. Hence, in figure 11, then reduces to here. There's no distance, there's no B. If the parameter L is chosen to be a half wavelength, then the input impedance of Z ohm, viewed as a half wavelength away, is Z ohms. L is designed to be a half wavelength for this reason. If the waveguide slot antenna is designed in this manner, then all of the slot can be viewed as being in parallel. Hence, the input admittance and the input impedance for an n-element slotted array can be calculated by this equation. Y input is equals to n y sub s. Z input is equals to 1 over y sub y input. The input impedance of the waveguide is a function of slot impedance. Note that the above design parameters are only valid at a single frequency. As the frequency departs from where the waveguide was designed to work, there will be a degradation in performance of the antenna. To give an idea of the frequency characteristic of a slotted waveguide, a sample measurement of S11 as a function of frequency will be shown. The waveguide is designed to operate at 10 GHz and it is fed by a coaxial feed at the bottom as shown in figure 12 here. Here. Next is the resulting S parameter graph is shown here in this following figure. Note that the antenna has a very large drop in S11 around 10 GHz. This indicates that most of the power is radiated away at this frequency. The bandwidth of the antenna extends from about 9.7 GHz to 10.5 GHz, giving a fractional bandwidth of 8%. Note that there is also a resonance at about 6.7 and 9.2 GHz. Below 6.5 GHz, the waveguide is below the cutoff frequency and virtually there is no energy radiated. The S parameter graph shown above gives a good idea of what the bandwidth and the frequency characteristic of a slotted waveguide that it will resemble. Next is the power handling capabilities of a slotted waveguides. Slotted waveguides are often used because they are capable of transmitting high power levels. To give an idea of what they are capable of, I will present a brief table of Gilden and Gould's handbook and high power capabilities of waveguide systems. Here, we will introduce some practical constraints of power handling capabilities versus the altitude. The maximum power is shown in Table 1. Here, Table 1. The max power is a function of altitude and will be further divided as CW or the continuous wave and 1 microsecond pulse. The CW column, here, the CW column, gives the maximum power handling capabilities of a slotted waveguide when the array is continuously transmitting in megawatts. The pulse column, here, the pulse column, gives the maximum power when the waveguide radiates a brief pulse and then shut off. Note that the power handling capabilities of a waveguide decreases with the altitude given in feet. The results are given for a typical X-band or about 10 GHz waveguide. Note that the power capabilities increases as the frequency decreases and vice versa. Note that the power decreases rapidly with altitude. This is necessarily constraint to keep in mind in designing radars for aircraft. Slanted waveguide antenna or SWA arrays offer clear advantages in terms of their design, weight, volume, power handling, directivity, and efficiency. So this is the end of my topic, which is the slotted waveguide antenna. Thank you. Thank you for listening.